the chat box.
Ma'am, I will share to the participants. Ma'am,
It's not thinking your voice is breaking.
can you share it to Kiran Sri sir so that the sir will share it to all our participants?
Okay, sir. Yeah. Yes, sir. Yes, sir. Sure. Sir,
Thank you, ma'am. Participants, now. Yes, ma'am. To the second session. Khanna. Welcome you, madam, to this faculty development. Ma'am, Khanna is an associate Indian Institute of Information Technology, Design and Manufacturing, Jabalpur, India. Her main area is biomedical image processing, dynamic gesture recognition, and UGC Fellowship, India, and a long-term JSPS Fellowship, Japan. IEEE Computer Society and a life member of IAENG. She has published more than 100 papers in of repute. She also published a book and many projects. She has organized various conferences and workshops at IIIT DM Jabalpur as guest editor for journals like Pattern Recognition Letters, ACM Transactions on multimedia tools and processing. We are glad to have you in this faculty development program to educate us on various advances in CNN. Ma'am, I hope you are muted.
Yeah, I'm sorry. To thank for this invitation and this warm introduction. Let me share my slides. Is it visible, my slides?
But we are not able to view as of now, ma'am.
The slide is not. Oh, is it visible now?
Yes, ma'am.
Is it visible now? But I have shared it.
Yes, ma'am. We are also getting the Khanna's.
Oh, but now I have opened it.
Screen, I hope it will get.
That is what I have done.
Oh, okay.
Yes.
Ma'am, but we are not able to see your content.
Now, are you able to see now?
Yes, ma'am. Now it is visible.
Thank you. So it's a topic in today's environment, that is applications of living in that era, and so we must be aware of this, because this is having lot of for researchers. So as my research area is image processing and computer vision, so looking at the title of the thought, let me introduce you the application of machine learning for computer vision, and start it with the computer vision. So I have taken it on the title slide. So object detection is actually one of the most vision, and especially once it is associated with self-driving cars, because the system multi-dimensional representation of road, and also object recognition of ways it is having. For example, you can use it for surveillance, say crowd monitoring, use it for a simple application like finding the interest of the customer in a shopping mall. Now, let's start with image classification as it is given here. Now, in this task, we have an image and the many different categories, let us say cat, dog, car, etc., etc. So basically, we want to answer the question. Now, here, if you see the picture, we are considering only one category in it. Now, locate where it is. So we'll try to locate our object in the picture. So the question now, my question is changing. The task is called object localization. Now, so far so good, but in a real life, I mean, we won't be interested in locating just one object, but in real life, there will be many objects in one image. So, driving cars, then we have to find out the location of other cars, traffic lights, signals, humans on the road. Type video, these are to be analyzed, and then we are supposed to take action on based on. Let's say on the road there is a paper ball or there is a paper bag. So once your car will be closer to it, because of the wind, it may stop. In finding all objects in an image and drawing so-called boundary situations where we want to find exact boundaries of instance segmentation. I would like to start my presentation and to tell you, because I have never been associated with the institute before. So I would like to tell you about IIIT, because we are, I mean, yeah, you can say, then we are having a small image and vision engineering group at our institute. Its applications and challenges. Some challenges you must be getting from this introduction only. Then how machine learning, and then my discussion will be focusing on convolutional neural network. So before coming to image and vision engineering lab, we are it's information technology, design and manufacturing of IT products, or you can say IT for design and manufacturing of products. We established in 2005. The Institute of National Importance in 2014. Four discipline only, that is computer science and engineering, electronics and communications, design. We are having a good collaboration, I mean, with Japan, and so we are having a state manufacturing, especially given by the industries which are we are associated with. So if you get a chance, please visit. This is about my lab. So what work we are doing. So we started in let us say this content-based image retrieval, then gesture recognition, then environment. Now, recently we were working on cancelable with the biometric as a state-of-the-art systems. The security of the biometric is become increasingly important. Today's now we all know that billions of images, and we are having so much data in our mobiles. That is why we need GB of data on our mobiles. So, but with these images, in fact, we can have huge numbers of information. And in the next couple of slides, I will show you the current state of the art. So, I will word of computer vision, and here you can see now every one of us is having on our mobile these days face detection camera, and not only face detection. In fact, lot much manipulation, not many filters are there, so that you may look it is security purpose. So at the let's say facility, you judge. Then this is your industry, the auto inspection. So now what is happening? The applications are in the farmer, or can take the image of his crop and may send to the and then he may be told what he can be guided there itself, that if with this what can be done. Then this is an old application where or handwriting recognition is there. This is your autonomous car. Then this is another app. I was seeing you are already having one lecture on that. So here in this picture, you can see that a girl is taking picture of his developed system, so that they can tell this about the skin cancer. So, and system is found to be giving equivalent performance as the board certified dermatologist. So this is something good which is happening, because now still we are having expertise. There is this class. You can see that at a mall, or you can say the camera is there, so maybe built to you. And here, this is, you can say that intelligent machines. So for doing now, this is not the end. These are just some applications. To tell you some more, you can see here this Mars Curiosity rover, which is Gale Card crater on Mars by the as a part of the NASA. Then we are having Amazon picking challenge. And here now with the earlier, what happens, you must have seen these pictures that when one now what is happening? The vision based things are going on. So yesterday I was looking at, so at the Google, they are developing this picking, but it is picking the objects. Like here also you can see that the particular objects they are picking up. Then the this VR and here some more are there, and then this is, you can see that from the internet pictures, our dense 3D model is your motion capture, which we have witnessed in many movies, many and appreciated also. So now researchers, this is what they are hoping for their children, that that this, so that the child sees anything, or a person sees anything on the, and just taking a picture and you are getting the, so that is the ultimate aim. But before moving towards other things, this example, this particular application is, let me tell you before moving. So now you can see that this is a cover of National Geographic, and here on this there a picture was Steve Mercury, and then what happens? It is being said that the two pictures belong to the. See, she is actually the Sharbat Gul. And this picture, the first picture was taken when she was 12 years old. At some the next picture in at a refugee camp in Afghanistan. So now the question is the same person. So now this person is identified, and here by her iris, the iris recognition algorithms, they are being applied on the 1984, and the other which was taken in 2002. I'm sorry. So the iris code was it was 0.24, and the right eye it was 0.31. Was observed that the odds of having the similar this thing, these iris pattern, that is in the right eye, and 10 to the power 15 to the 1 for the left eye. So that is how the National Geographic magazine and the picture is being printed. Now how it helps, and a lot of efforts have been made for educating the women in there, so that for the move to the vision. So it's a computer vision. It sounds very easy because we do it effortlessly, right? Since our child see that what is happening. So if you consider the two, human vision and the computer vision, so we see something. So our eyes capture the light. Here you can see, and our visual cortex process. Thought about how your eyes coordinate with your brain. So it is actually a and balanced pieces of a system, because that is how we have evolved, which help us to do things as simple as finding in the phone. So, but what happens when we take pictures with camera? So we are just getting here our sensing device. We need a camera. There it was an eye, and then here interpreting device was brain, and here this is your computer. Okay, we get just a bunch of colored dots, right? Colored dots, which we call pixels. So now we want to make like we say we are doing it effortlessly, so it should be easy. But what happens? It is, let us see why. Look at this picture. So what we are trying to say that every image is actually telling a story. Now, if you look at this picture, I mean, you can see various, I mean, person here, the instrument here. So, okay, object recognition algorithm or your object recognition method, so that you are identified, okay, C is there, which is who is playing a chord, right? Then this is what is the state of the art, right? Now we are able to detect the object. But what happy with this information that the person backs bench, but person C step back or not. So this type of information we want. Just let us see our goal, right? This is the goal of the computer behind the picture. Now, if you look at this picture, this is a famous picture from Paris where this engine got derailed, and right, computer just has these numbers. So, like, can that, okay, this is a picture from Paris where in this year this has happened. I mean, it is not possible, right, to get this thing from this data. See, and this is what computer gets, right? So here, what is the goal here? If we want to achieve our goal of perceiving the story, we need to bridge the gap between the pixel and its meaning. So now the question comes that can computer match human? Yes, as well as no. So if you talk about 1 decade ago, it was surely no, but now there are many applications where, I mean, computer percent accuracy, right? So we can say that a huge success is being made in the past decade, and that is due to deep learning. So that keeps on changing. You can see that there are many ways here. You can see that one object, but different view. Intra-class variation, you know that for any object, right? N number of objects are there in any class, but it is very easy for us, not that for computers, right? So intra-class variation is there, motion, then illumination. Apart from that, more challenges, you can say background clutter. Here you can see that these are the background clutter, then occlusion, only partly visible. So problems are there, which makes the job difficult. So now the question is, can we call a system? So yes, bird and aeroplane. So if you consider, then there is a same underlying principle. Senses, and the two eyes gives us a data rate of about 3 GB. 1/3 of our brain is devoted to processing the signals from our eyes, and but still we don't understanding of how our visual system works. And once we do, then we will be able to provide vision to blinds. Our visual system. So here now, just for a comparison, what happens in our, if we talk about vision, so this is the neurons, right, we have, and so I mean, but it's still long. And yesterday only I have updated this data, so it says that in GPU the highest is possible or not possible. As I told you that because of the growth in the many things are possible. Comes the role of machine learning, right? So now how they think about it, this simple idea comes because earlier when we entered into the field, we know that we have written the fixed, programs like, we realize that we are all learning things, right? So how do we learn? We learn that why not our computers may learn with this examples, right? So that is how machine learning came into the without explicitly programmed, right? So here again we are learning from experience on the data. Since last couple of days you are going through this, so we know that it is a training and testing are being shown to your model, and that is how your model learns, and then it works on the unseen data. The training is the process of making the system able to learn. So now if we talk about then machine learning systems, they begin with a top-down prediction of can say features, right? But then it comes the curse of dimensionality. So what is happening with the fixed power of a classifier or a regressor increases first as the number of increased, but then decreases, right? So with this, then there comes deep learning models. So on its head. So the deep neural network training process uses massive data to teach the machine. So in general, we can say that it produces a model to previously unseen images to predict. Right? So that is what is the difference between the traditional model and the deep learning model. So what we are doing in the deep learning model, basically, of feature extractor. Each layer here, so from the image, what now from these pixels, what happens that it provides DL gives you a double network where each layer in this hierarchy is extracting features from output of the previous layer, right? And these nearly same structure, and they are trained jointly. CNN, right? Convolutional neural network. So in the past, classification process. So a picture of pixel of image, they are being fed as input, and the whatever. So what happens here? You can see this uh, in the past decade. This DL has proved a large amount of data. Right? So so one of the most popular deep learning network, convolutional neural network, and in fact, since the 1950s, the early days of artificial intelligence, researchers that can understand visual data, right? And that is how the field of the computer vision evolved. But in 2000, vision took a quantum leap when a group of researchers from the University of Toronto, they developed an AI model that surpassed algorithm, and that is also by a huge large margin. So with this was this AI system, which is known as the AlexNet, named after its creator, Alex Krzyzewski. So CNNs were first developed in the 1980s, but as I told, as now you know that they require a lot of data and enormous processing power. So they could used, right? They could not be included into the machine learning world at that time. But later on, with the ability of data around 2002, the group came with a data set that is ImageNet, where millions of images were computing power. The CNN came into the picture, and this was the first. I mean, you can say that this is actually the example from where it has I need to tell you the basics of CNN. So before that, let us see. So what is, we say that we are going to this is the, like, what is this? You can say that CNN layers of artificial neurons. So we have in our brain neurons, and here they are perceptron, right? So artificial, you can say multiple layers of, they are mathematical functions that calculate the weighted sum of multiple inputs and outputs value, right? Now, when you CNN, each layer generates onto the next layer. Here you can see that so this, you can say, or one hidden layer network, usually input layer is not counted here. So here this is just a simple that being given to these you can say perceptrons. Why this is called hidden layer? Because unlike input and output layers, state of the hidden layers are not directly observable, right? Provided by us. So we are providing input, and the features are being learned. So what is the process here? And we are going to present a training pattern, right? And that training pattern get an output, and this output will be compared with the actual value. So if output, so be quite maybe far from the actual, so the loss is, so that which we have initialized randomly, these weights are supposed to be adjusted and updated. Will be repeated to reduce the error. So once we are saying, okay, the error network is trained, and when this network will be learning this as it was there on the previous, where you can see that in the first layer it is learning edges, then object parts, then the objects, right? So this is how it will start learning. Now the network for image data. Okay, so now suppose, right? So image database. So these images are supposed to be passed to this neural network, and we need to classify. Let us say that okay, let us say my picture is of 256 cross 256. So what will be the 6 cross 256? So your input size of the input layer will be this 6. Now it says that, let us say we are having this hidden layer. In this hidden layer, here you can see 4, but let us say we are weight parameters we need here. So 102, right? Remember that here what was the size? Your 250. Here there are 1024 units. So what is what it becomes? 256 cross 256 cross 102. And here, so let us see, if you look at there, 256 cross 256 into 10 data, and we know that not many such layers will be there, and multiple times these layers there, they will be, the weights will be fine-tuned. So what happens? So here the because just to avoid how can we make things faster? Yeah. Then these are, let us say, these are the pixel values of a block of an image, right? Now, when we will observe it, then we high dimensional data, but later on we can identify that here there are some redundancies, right? So this data is having redundancies. So those patterns are what we wish to have. So the main question is that if you just consider this perceptron in this hidden layer. So you can see that lot many connections, right? This is a fully connected. We have a smaller network. That is what is happening in CNN. The question comes: do we need have and also when we say about weights, so can some of the weights be shared, right? So this is the CNN. So CNN are just neural networks with 3D activations and weight share, right? So weights are being shared. We having this fully connected model. We go for image understanding, then patterns. If you see the color as compared to image size. So if you take this example that let us say we are having an eye detector filter. Detector can be used in place of the entire weight. Need to go for the entire weight parameter matrix, use a small pattern detector. Now, then what happens? It is also observed that some patterns in the image, the same pattern. For example, again, if we take previous this eyes, right? So eyes are present at different positions. Once we have this eye detector, now no matter how many pair of eyes, right? How many eyes are present in the picture, we will be pattern detector can be moved around and detect eyes at different positions. So with this so we know that we are going to make use of parameter sharing, and here when we say small pattern detector, those small patterns for the entire image. And how? So what we are doing in CNN, we are actually pattern detectors. We are learning these filters. So these filters are learned through the neural network training in the same way as it is done. And just like we were having in the earlier neural network, we were having hidden layers. We will be having here convolution layer. And to handle this large size of image data, the pooling layers are introduced. So all layers. Layer, then it has a number of filters that perform. You can say take this example of your eye detector. So you can see this eye detector. This is a filter. This is your input. Okay, if there is eye present here, so that is how, or this filter is going to produce a response here, and that is how it performs the convolution operation. Aware of this convolution operation, let me discuss. So here, let us say this is a filter, right? So your filter is small pattern, right? So your filter is small as compared to this image, and when we perform convolution operation, we of the picture, and what we do, we take sum of 5 will be multiplied by 1, 1 will be multiplied by 0, 7 will be multiplied by -1, and that is how you is produced by 10. So in the output of the convolution operation, value will be written as 10. Now what happens, as we know that this pattern is going to be moved. Value 5 will be replaced by value -70. Check also the corresponding the corresponding coefficients, they are going to be multiplied and added. And one pixel down, again it will start from here. That is the entire image is covered. Talk about the images. If you are having three channels, red, green, and blue. So when we talk about images, color image, red, blue, and green channels, it means that every with the filters, right? So you can see that these three channels are there, and accordingly we will be having filters. So because if you look at this convolutional layer, then that is 32 cross 32 cross 3. 3 is for R, G, and B. Now this is your filter, that is a small pattern, 5 cross 5 cross 3. Filter, you need to have the full depth. So the depth is 3 here. So here also the filter depth will also be 3. Now process, so we will convolve the filter with the image. That is, so we will slide the filter over the image and compute that. As I told you, the filters will always be extended to the full depth of the input. So this one number, right? So when you are going to multiply, so this is your filter comes a new term, that is, you can say bias. So bias is actually used to it allows to shift depending upon the, I mean, regardless of your input. So that is how bias is there, and so this will give this is going to give you and this process will be continued for all the pixels. Number, this is actually a hidden neuron in the next layer. So let us see, this is your input. Now this thing, now this gives you the one actually gives you 3D activations. How? Because you know that this your data channels are there, right? So when you are saying not only X but 1, 2, and 3, right? So red, green, and blue. So that is how you are going to, that is how you get the output. So that is, you can say that it is sum over the 3 axis. One hidden neuron. Similarly, what happens that you will be using another filter. So another filter that will give you another response to get here these two output neurons, right? For, let us say, filter number 1, the second generated with that. Similarly, what happens that vary, right? So we want to use n number of filters. So filters, those vary response will be produced. So here you can see that this is your depth damage. So it means that 5 filters you are using. Say this 5 cross 5 cross 3. On adding more number of filters there, right? That each neuron has its own 3D filter and its own scalar bias. So that is what we have done. Own bias. So each neuron is distributed across the input. Here we have shown it for center pixel here, where you are placing that filter, right? So you are getting this value. Now this filter will be placed on each and every pixel here, right? And that is how these values will be generated. Now this is which is being done in the, we don't need all those many weights, right? Here weight shading is being done because now those 3, these filter weights, they are shared, right? So if you are placing your filter here, then also the same coefficients will, the same filter, each filter shares the same weights, right? Now here you can see this, you can see that all the pixel values, they are arranged in the form of a column array. So what happens here, like so these 3, let us say, because your filter is, let us say, 3 cross 3, so this is how these pixels are going to be involved. And then when you are moving your weights, because the filter coefficients are same, so again you can see the next number. So this is how you can match with the colors, they are going to get. weight, right? So that is what we mean by the weights. Now again, come back in you are having this D sets of weights. So basically, yeah, weights, right? So here we are using D sets, so D filters. So connected. So now what happens? Again, let us see. You can say that this in the output volume. So this is going to produce just one output, right? To form one output of one filter, right? So one set of weights will give you one slice in this. Let us say if you are using D different filters, so you are going to get these slices here, right? So first slice. So in practice, convolutional 64, I mean, that is very common. These weights are 4-dimensional. How? Output depth. So here now what happens? Not only convolution, because we know that how our brain we are supposed to use an activation function. So whatever is the output here, convolution output of the activation functions, right? So CNN is what? Basically sequence of convolutional layers. See that convolution layer plus ReLU activation function. This is your ReLU activation, right? So for 0, but for these values of X, output is same. So there are, when you go through the literature, there are many activation functions, but this is one of the most common. Right? So the output will be, because we know that the neuron, it is not like a linear output, right? Introduced with the help of activation map. So the convolution, whatever is produced, that is being passed to this activation function, and that you can what is there in this 3D cube. So I say in this example, this is your image, and these are the 32 filters, right? And each of these filter is of size 5 cross 5. This filter will give you one depth slice, right? So 32 slices we are will give you first slice, second filter, second slice, third filter, third slice, and that is how these slices are being arranged, and you will get the output volume. So then second okay, fourth one, then this is, you can say, the last one. So that is how you are getting this output. That one filter is or you can say one depth slice or activation map, you can say. Output. So you can say that some of the filters, they are detecting all. It means that the number of filters can be extra and can lead to redundant information also. But at the same time, number of filters, then it may lead to loss of pattern information. So that is why it is better to use large number of filters. Information loss. The how these filters are being learned. So I told you that the filters are being learned, and each filter is learned to detect a small pattern. And these filters, so what happens randomly. So in the beginning, the filter values are chosen randomly, and gradually these values, right? So this is how what happens. So just a recap. So you can see that image, this is your filter, you are getting the feature map, right? Now second set of weights give you another, like this is by using different number of filters. So here you are using 6 filters, so you are getting 6 activation maps. demo of this at the Stanford. I request you to see those. Now, what is happening here? Your image was of size 32 cross. Okay, first of all, let us see. Now, you are, let us say this is your 3 cross 3 filter. So the weights are being this. What happens when your it's are sliding and generating output? Then what happens here? In a 3D sum, remember, right? Because RG and D3 channels are 3D sum, and then the bias is there, right? Now, here what happens? One position forward, right? But what happens? We can also convolve with stride, right? So that now what happens that it is moving 2 position forward, right? Earlier it was moving 1 position. Now it is moving 2 position forward. So we can notice that, let us say in this picture, so if it was 2, then okay. If it is 3, then what happens? Ultimately, the filter will not be able to cover all the inputs, right? And the output of the output, and sorry, this is your input and this is your output, right? So output becomes this convolutional layers and image dimension. What is the relation? Now here, if you can see that you are 32. You are using this 5 cross 5 filter. So ultimately, what happens when the so that the complete filter is on the image. So in the process, what happens is that when you are going to place this filter here, the center from here, right? Similarly, when you will go here, then when the last 2 pixels remain, we can't place filter there because of the image, right? So when this filter is inside this picture, so what happens here? The dimension is reduced. So now instead of 30 to 28. Now what happens if this process continues? Because we are using many filters, and if this process, image size is going to be reduced, right? So what is done? So if we consider here, let us say 56 cross 2, 56 cross 3, and there are 8 filters, right? Each of size 5 cross 5. What will be the output? Is of size 5 cross 5, but the depth will be taken as the depth of the image. So each 5 cross 5 cross 3 filter volume, right? And then it will be convolved to each block of cross 3 in the image, and it will give you just one output value. Okay. So whole computation, whole convolution process with one filter. So let us say 2 and 2, 4, right? So 4 from both the sides and up and down. 256 cross 256. Now your image is of 252 cross 250. Okay. So when using 8 filters, so my final output volume will be 252 cross 252 cross 8. So from 256 to 250. And this output dimension is related. F. Now, what will be your output size? So if you are keeping 1 pixel forward, right? So in fact, what happens that with this notation, with this understanding, we can simply have a this size of the filter, size of the image, stride, and what is the output volume we will get, right? So let us say if picture 7 filter is 3 cross 3 and stride is 1, what will be the, you can check from this that okay, if the stride is 1, minus 3 by 1 plus 1. So the size will be, taking stride as 2, then what happens is 3. So you can see that the stride is increasing and the size of the output is decreasing. As I told you that we will be having many layers, right? Not one layer. So here you can see that here this is one layer of convolution layer and using radio activation function. So your image converts to from 32 to 32 to 28 cross filters. Now here you remember this thing. See, the filter depth and the input depth should be matching. So here your filters were of size this 5 cross 5 cross 3. Now, so now your output is 28 cross 2 into 6. Give you one slice. So next time what is happening? Next time your filter will be 5 cross 5 cross 6 because now the depth is 6. Then this to be reduced and this is going on as you are using more number of layers. So what to be done? I told you many layers you are going to be using. So the this zero padding is used to control the dimension reduction. So when you are taking so the last pixel was not participating. Last input pixel was increase one layer of 0, right? So this is zero padding. So when it will be 5 cross 5, then 2 layers of 0. Like example, when your input image is of size 7 cross 7, your filter is size 3 cross 3. What will be your output? So you can, I mean, because time is less, you can have this as simple as we have discussed. Suppose your input volume is 64 cross 64 cross 3, and then you are applying 10 filters of size 5 cross 5. 2, and so because 5 cross 5, so padding will be 2, right? And your 5 is 1. Then what will be the output volume? So what will be the output volume? Calculate, that is your 64 minus 5 plus 2 cross 2 divided by 1 plus 1, that is your 6. The number of parameters, that is 3 plus, remember, one bias term was also there. How many parameters are required to be learned? 10 filters, so 76 into 10, that is 760. So with this help, what happens that you can always to derive with this discussion, so that you can have this right, this know the convolutional neural network. It is what does it mean? This is your fully connected. Here you can see that each input, right, is connected, right, with each of the convolution. Here you can see this. Okay, so let us say these numbers are being arranged. So what happens here? When you are going to put this, then what happens? This filter is going to produce output 3, right? So produced these weights and using these values, right, which I have told you earlier also. Now when this so here we can say that only 9 inputs, right? It is not connected to each and every input like there here. Do this 9 inputs. Similarly, when you go for next, so is not fully connected, so that is why I mean there are fewer number of parameters, right? Similarly, that this is how, because same filter coefficient we are using, so this is how the weights are being. This was And we are getting that not fully connected, another is shared. So that is how that the picture is there, convolution layer with activation, and pooling layers are being introduced here. There is a fully connected, right? We are having a fully connected. What do you mean by pooling layers? Because so what happens, we need, when your image is of large size, then we need to compress so that the input and output volumes of layers may be, so just give me 2 to 3 minutes. So pooling layers actually helps us making representation smaller, and so that's, so here you can say that this is your pooling layer. So it is, you can say that like downsampling. So this was your 64. When you are doing this pooling, then this becomes half of it, right? So what happens? We use max pooling. So what do you mean by max pooling? Let us say we are this right? Set, right, where our filter is placed. So in the max, out of the 4 values, the maximum one will be kept. Now, when we are going to have average pooling, so out of these, you are going to keep the minimum value, right? So that is how the just size. So you can say that the pooling is some sort of subsampling. So here, when you do pooling like subsampling, you say that you are not losing image. The pooling helps us to have fewer patterns to extract patterns. We have come to a generic CNN architecture. So here you can see that convolution layers are there, and so when you do this max image with the activation function, then max pooling again, and these may be network, and that is how. So here, so all the things we have discussed, just one thing, that what happens at the end. So this flattening operation, right? So what happens here? So here, what happens? That is values, and finally they are being flattened here, and then these values are passed to the, like here you can see all these values. These, okay, they are passed to the feedforward network. And here this is your convolutional network. In between pooling layer is there, and at the end it is fully connected. And the network is able to identify or classify these objects, right? So here the convolution filter, they right is one, pad is one, like that, right? So it's a similar process which I discussed. So these are the basics of the this just to summarize this, the number of connections are reduced, pooling layers are compressing the output volumes. So that is how we are getting the equivalent representation, right? Happens that we are having ability to work with the inputs of variable size. Okay. And but there are several parameters on which, remember, this is roughly speaking, we can say that architecture, and you are defining it so that the loss is minimized. So what you can see that if you just network architecture, initialize the weights, as I told you, so that you can, ultimately you need to minimize the loss and monitor progress, right? So here you need to, so what are the things to fiddle here? The network architecture, which architecture you are, which CNN you are going to job. Type regularization, because it reduces over, so many are there. Then weight initialization, because so many things, so many fitter. As I told you, LXNet, VGG, RESTNet, these are all thing is industry deployment. So now with this enormous major organizations are using it. It is being used for variety of purposes, not only for image recognition, speech recognition. Definitely the training takes a lot of time, right? Many times it takes days, weeks also. But run time, test time, it is taken, followed much in the beginning, a couple of minutes, and that is how it is spill over. Hearing and
Yeah, thank you very much, madam, for introducing different. There, we've gone with machine learning. From there, with convolution neural network, and you clearly explain about what is pooling, convolution, and everything with an example. You clearly explain now. So, thank you so much for your clear explanation.
I good and only it's of some purpose.
Thank you so much, ma'am, for being part of. On behalf of our Sri Vishnu Engineering College for Women, we convey our gratitude to you. Thank you so much.
Thank you. Thank you.